Welcome to calculus.
We overcomplicate even the simplest task.
On this episode, Stevenson will demonstrate
there is a process that's outlined in the textbook that gives you a step-by-step protocol that you can use to help create related rates equations and then ultimately solve a situation that's given to you. We're going to follow that model in this example here. So here's the problem. Let's go through it and annotate as needed. So we have a hot air balloon rising straight up from a level field, is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So the first thing we want to do to help us understand this problem is to create some kind of picture. Notice we create a right triangle. So this is the angle created by what the rangefinder is tracking and the ground. Now we have some kind of a picture here. Now notice h represents the height of the balloon from the ground. And we also have some other numbers in here. So let's add in what we know. We know the rangefinder is 500 feet from the liftoff point. So this distance is the rangefinder from the liftoff point. And so this is our angle created with the ground and then what the rangefinder's direction of tracking is, essentially. So what it's saying is, it says at the moment the rangefinder's elevation is exactly pi over 4, they're telling you the rate of this angle is increasing at a particular time, and it's asking us, well, how fast is the balloon rising? So I want you to imagine this. So as the balloon is rising, right, this height is increasing. Well, this angle right here is also increasing, okay? So the rangefinder is tracking the object as it's moving. So two things are changing with respect to time. That's why this is a related rates question. Let's look at what the question's asking. It's asking how fast is the balloon rising at this particular moment? And the moment is when the angle is exactly pi over 4. So it's asking us, so what are we trying to find? We're trying to find how is height changing with respect to time. So I'm going to call that dh dt. How does height change as time changes? So that's what we're looking for. Well, we need some kind of equation that can connect these elements here. Now notice this is a right triangle. And if you remember your trig functions, we can use tangent of the angle to connect these sides. So tangent is opposite over adjacent. We now have an equation here that connects the angle to the height. But remember, what is it asking for? It's asking for dh dt. So what we're going to do now is we're going to isolate h and make this equation with respect to h. In order to do that, I would multiply by 500 on both sides. So 500 times the tangent of theta is h. At this point, you might be thinking, well, okay, Stevenson, just put in pi over 4 and we're done, right? Well, not exactly. Remember, the angle is changing as the height is changing. So what we're going to do is we have an equation that connects or relates the angle to the height. So now what we're going to do is we're going to apply the derivative to this expression with respect to time. Remember, this is what we needed, right? We were trying to find what is dh dt. In other words, how is the height changing as time is going on, because the angle is also changing. Now, a suggestion I make is once you have your equation and you've taken its derivative, I want you to look at any other variables that still exist in here. So here's what I mean. I have dh dt. What else do I have here? I've created a d theta dt. So that means how is the angle changing with respect to time, and I also still have the variable theta. Now, why do I do this list? I do this list because it helps me keep track of all the information that's given to me. So let's go back and look at our problem here. So we're trying to find dh dt. So in other words, we're trying to figure out how is the height changing with respect to time at a particular moment. Well, let's go back and read. What's the moment? At the moment, the rangefinder's elevation angle is pi over 4. Okay, wait. Pi over 4, that means that must be theta. So pi over 4 is theta. Excuse me. Yeah, it's theta right there. Okay. Next, it says at this moment, the angle is increasing at 0.14 radians per minute. Okay, that's a rate of change. See how it's radians per minute? It's change per time. So that means that's going to be one of the dt's. So if you look, that's going to be d theta dt because that's the angle changing per time. So 0.14 radians per minute. So we have everything we need. Now, when you do your list, a little tip here, when you do your list, the only thing that should be left unknown is what you're trying to find. If you do your list of all your terms and you have more than one thing missing, go back to the problem, read it again, and see if you've missed some sort of number, or you might have to do an extra formula or calculation to find a missing value. You'll see one of those in a later example. So I have all my values. What I can do now is take this information and plug it into this equation right here and find my answer. At this point, grab your calculator and get an answer. Now, I got 140 from my calculator. What are the units here? Well, it's dh dt. So h, the height, is measured in feet because we can see this distance here is in feet. And the time, the dt's, we can see the rates were given to us in minutes.